Dear students, today let us learn the water technology. Introduction. Water is the most common liquid on our planet, vital to all forms of life. Water covers 71% of Earth's surface. Among three essentials of life, water occupies the second place. Human body contains 65% of water in the form of blood and other body fluids. Sources of water. There are two types of sources of water: surface water sources, underground water sources. Surface water sources: rainwater, river water, lake water, sea water. Underground: spring water, borewell, and well water. Impurities present in the water sample have been classified into three categories: dissolved impurities, for example, bicarbonates, chloride, sulfates of calcium, magnesium, sodium, dissolved gases such as carbon dioxide, nitrogen, hydrogen sulfide, ammonia, etc. Suspended impurities. There are two types: inorganic suspended impurities and organic suspended impurities. Examples of inorganic impurities: clay, silica, oxides of iron, manganese, etc. And organic suspended impurities like wood pieces, particles of dead animals, leaf, fishes, bacteria, algae, etc. And third category, microscopic impurities. The microorganisms makes the microscopic impurities which spreads the waterborne diseases. Let us learn how to determine the dissolved oxygen content present in the water sample by Winkler's modified method. What is dissolved oxygen? Dissolved oxygen is nothing but the atmospheric oxygen dissolved in water, and it is measured in terms of milligrams per liter or parts per million. Algae and rooted aquatic plants also give out the oxygen into the water through photosynthesis process. Oxygen content of natural water varies with the temperature, salinity, the photosynthetic activity of the algae, and higher plants and atmospheric pressure. Reduction in dissolved oxygen levels causes anaerobic condition in water and adversely affects the aquatic biota. What is the principle behind this dissolved oxygen determination? To determine the dissolved oxygen content in the water sample, we need an oxygen carrier, and oxygen carrier can be obtained through a reaction between manganese sulfate and potassium hydroxide. So when manganese sulfate is added to the water sample in strong alkali medium, MnOH twice manganese hydroxide is formed, which is oxidized by the dissolved oxygen present in the water sample to form MnOH twice basic manganic oxide, and this basic manganic oxide acts as an oxygen carrier here. Tetravalent manganese reverts to divalent state in acid media with the liberation of oxygen, and the liberated oxygen reacts with the potassium iodide to liberate the iodine, which is equivalent to the dissolved oxygen content available in the water sample. The liberated iodine later is titrated with the standard sodium thiosulfate solution using starch as an indicator. And these are the reactions here. Manganese sulfate is made to react with the potassium hydroxide to produce manganese hydroxide, and this manganese hydroxide reacts with the dissolved oxygen content present in the water sample to produce basic manganic oxide, which is a brown color precipitate, and it is allowed to settle down, and this basic manganic oxide is dissolved in sulfuric acid medium to produce the atomic oxygen, and this atomic oxygen made to react with the potassium iodide in presence of sulfuric acid medium means the oxidation reaction takes place here to produce the iodine equivalent to the amount of dissolved oxygen present in the water sample, and the liberated iodine is titrated against sodium thiosulfate using starch as an indicator to get the Britt reading, and then dissolved oxygen can be calculated. This is Winkler's method. Now, what is Winkler's modified method? In Winkler's modified method, azide solution is added here. What is the need of this azide solution? Because in some water samples consisting of nitrites, These nitrites may oxidize potassium iodide to iodine, and excess of iodine can be liberated here and than the dissolved oxygen content present in the water sample. And therefore, to avoid these erratic results, sodium azide is added here so that this sodium azide destroys the nitrites in the water sample, thereby reducing the error. And these are the possible reactions with the addition of sodium azide here. And what is the procedure to carry out the dissolved oxygen determination? Take exactly 300 ml of water sample into a glass toppered bottle. To this you add 3 ml of manganese sulfate, 3 ml of alkaline iodide azide solution. Stopper the bottle and shake it well and allow the brown precipitate to settle down. Later you add 1 ml of concentrated sulfuric acid slowly, dropwise. Shake it well until all the precipitate dissolves. Then 100 ml of this prepared solution is pipeted out into a clean conical flask and titrate against sodium thiosulfate, standard sodium thiosulfate solution, using starch as an indicator. Record the volume of sodium thiosulfate required for the titration. Now this is a calculation. Calculation is simple: N1 V1 N2 V2. N1 V1 for the water sample, N2 V2 for the sodium thiosulfate. The normality of oxygen present in the water sample can be calculated by knowing the normality of sodium thiosulfate, and the volume of sodium thiosulfate consumed is nothing but the burette reading divided by total volume of water sample used for the titration. That gives you A. Then mass of the dissolved oxygen per liter can be calculated here. Normality obtained from the first calculation, normality of oxygen into equivalent mass of the oxygen. So that is A into 8. 8 is the equivalent mass of oxygen, and multiply by 1000 to convert it into milligrams. So you get the dissolved oxygen content in the water sample in terms of milligrams per liter or ppm. Now let us learn the biological oxygen demand. How to determine the biological oxygen demand present in the wastewater sample. Biological oxygen demand means it is the amount of dissolved oxygen required by the aerobic biological organisms in a body of water to disintegrate the organic material present in the water sample at a certain temperature over a specific period of time, that is 5 days. Biological oxygen demand can be determined by Winkler's method. The Winkler's method already we have learned in the dissolved oxygen determination, and the same principle is being applied here to calculate the biological oxygen demand. Microorganisms such as bacteria are responsible for decomposing the organic waste. When organic matter such as dead plants, leaves, grass, clippings, manure, sewage, or even food waste is present in the water body, the bacteria will begin the process of breaking down the waste. When this happens, much of the available dissolved oxygen is consumed by the aerobic bacteria, robbing other aquatic organisms of the oxygen they need to live. So BOD is a measure of oxygen used by the microorganisms to decompose this waste. If there is a large quantity of organic waste in the water supply, there will also be a lot of bacteria present working to decompose this waste. In this case, the demand for oxygen will be high because of all the bacteria, so the BOD level will be high. As the waste is consumed or dispersed through the water, BOD level will begin to decline. So let us learn how to determine this biological oxygen demand present in the water sample. And this is the Winkler's method as we have studied now in dissolved oxygen content determination. Same reactions. We'll go to the procedure directly. A definite volume of sewage water is diluted to a known volume, and then this water diluted sample has to be equally divided and to be filled in 2 BOD bottles. The first bottle, the dissolved oxygen content has to be determined immediately, and the second bottle has to be kept for incubation period, that is for 5 days at 20 degrees centigrade for the growth of bacteria. So in the blank titration, 2 to the water sample, collect in the blank titration, 2 ml of manganese sulfate solution and 3 ml of alkaline Ki solution are added to the first bottle, stoppered, mixed well by shaking for 10 to 15 minutes and allowed to stand for 2 minutes there. Later, 1 ml of constant sulfuric acid is added to dissolve the MnO2 precipitate. And later, a known volume of this solution is titrated against standard sodium thiosulfate solution using starch as an indicator till the discharge of the violet color. The second sample, which was kept for 5 days at 20 degrees centigrade, is to be taken out, and the same procedure is carried out as like in the blank titration. The burette reading obtained in both the type of titration is used to calculate the dissolved oxygen content D1 and D2 respectively, and then BOD is calculated using an equation called D1 minus D2 divided by A and B, where D1 is the dissolved oxygen content in milligram per liter obtained in the blank titration, and D2 is the dissolved oxygen content in milligram per liter obtained in the sample titration, which was kept for 5 days 20 degrees centigrade. D is the volume of water sample before dilution and B is the water sample after dilution. Now let us determine the chemical oxygen demand in the water sample. Chemical oxygen demand is a measure of oxygen required to oxidize all the impurities or all the compounds present in the water sample. That includes organic and inorganic impurities or compounds. The basis for the COD test is that nearly all organic compounds can be fully oxidized to carbon dioxide with a strong oxidizing agent under acidic conditions. COD is generally expressed in terms of milligrams per liter or parts per million. What is the principle behind this determination of COD? A measured volume of wastewater sample is refluxed with a known quantity of potassium dichromate solution in acidic medium in presence of silver sulfate and mercury sulfate. The oxidizing agent potassium dichromate oxidizes all oxidizable impurities. Silver sulfate catalyzes the oxidation of long chain organic compounds, aromatic compounds, etc. Mercury sulfate avoids the interference of chlorides by forming soluble complex with them. The amount of unconsumed potassium dichromate is determined by titration with the standard ferrous ammonium sulfate solution, and the amount of potassium dichromate consumed corresponds to the COD of the sewage water. What is the procedure adopted here? Again, here also two types of titrations like BOD, sample titration and blank titration. First, let us learn the sample titration here. A known volume of wastewater sample is taken into round bottom flask. To this, 1 gram of mercury sulfate and 1 gram of silver sulfate are added here, followed by a known volume of potassium dichromate acidified with the dilute sulfuric acid. Then the round bottom flask is fixed with a water condenser and contents are refluxed for about 2 hours. Then the contents are cooled and titrated against standard ferrous ammonium sulfate solution using ferran as an indicator till the color changes from blue-green to red-brown. Obtain the burette reading here. Then go for the blank titration. Blank titration, the same procedure of sample titration is followed here, but instead of wastewater sample, instead of sewage sample, equal quantity of distilled water is being used here. Then obtain Biot reading here, and using the Biot readings in sample titration and blank titration, COD value can be calculated here. This is a calculation. N1V1 N2V2. N1V1 use it for the wastewater sample and N2V2 for the ferrous ammonium sulfate. Now normality of wastewater sample N1 can be calculated by knowing the normality of ferrous ammonium sulfate and B minus A. What is B minus A? A is the volume of FAS used during sample titration and B is the volume of FAS used in the blank titration. The Biot readings in sample titration and blank titration. So amount of potassium dichromate consumed in terms of ferrous ammonium sulfate can be calculated by subtracting B minus A. So that is the exact volume of potassium dichromate required for the neutralizing FAS here. So normality of ferrous ammonium sulfate into B minus A divided by volume of wastewater sample used for the titration. So COD of the sample can be calculated here. Normality of wastewater sample, that is above calculation, multiplied by equivalent weight of oxygen, that is 8, and convert it into gram into milligram, multiplied by 1000 here. So COD of the sample can be calculated using equation normality of ferrous ammonium sulfate into B minus A, Biot readings in blank titration minus the sample titration into 8 into 1000 divided by V. So exactly what is the difference between COD and BOD? BOD is nothing but the amount of oxygen required to oxidize only biodegradable organic matter present in the wastewater sample using microbes, and COD is the chemical oxygen demand. Here the dissolved oxygen content here amount of oxygen required to decompose all the type of impurities, organic and inorganic type of impurities, or biodegradable or biologically non-biodegradable organic matter present in the wastewater sample. So hence COD gives the entire organic matter decomposed. COD gives the entire organic matter, whereas biological oxygen demand gives only the biodegradable organic matter. So hence COD values are always greater than the BOD values here. And you need to solve numericals based on this COD, BOD and dissolved oxygen content. Thank you.